Alright, hey everybody, sorry about earlier with the Zoom. Yeah, on Wednesday I'll be somewhere with a good Wi Fi connection, so I can answer questions and everything. But yeah, feel free to email me or message me on Canvas with your questions, and I can go over some problems you have questions about or whatever on Wednesday. For now, I'm just going to do these two problems that were posted by Dr. Nard in the announcements as review. If he ends up posting um, like um, some more review problems or old exam problems, I can go over those on Wednesday as well. Or I'll just if no one if I don't hear from anyone or he doesn't post them, I'll just find some problems to go over. So that's how I'll work that. Yeah, so I apologize again. So I'm just going to get started. Um, And so for this first problem, it's just asking, uh, so it's a reversible reaction, A goes to B and C. It gives you the equilibrium constant, the enthalpy of reaction, and the Ca naught. It's pure A that's fed, or in the problem. It's also elementary. I don't know if that's mentioned, but I assume it's elementary if it's given like this and it's not explicitly stated. So to start off, it's asking us to find x equilibrium as a function of t. So the first thing we need to do is to um, find the equilibrium constant as a function of t. So in order for us to do that, sure, black. Okay. And then, so our Kc of t is going to equal Kc at 300 Kelvin times E to exponent our delta heat of reaction or enthalpy of reaction divided by R times 1 over 300 Kelvin, which is our temperature, first temperature, and then minus whatever our second temperature is. Nope, yeah, another. There. Okay, so then we can plug in what numbers we do have. So we have that the Kc at 300 Kelvin, that equals 1 mole per, I think, or is it, oh, it's liter per mole. Mole, exponent, and we're going to convert our delta heat reaction to calories per mole instead of kcal, just so we can have our gas constant easy conversion. So say negative 39,740 divided by 1.987 calories. Calories per mole. This is calories per mole Kelvin. That's times 1 over 300 Kelvin minus 1 over cellular temperature. Alright, so we can just so this is going to, sorry, make that a little neater. So this is going to just basically equal so this will just be negative 20,000 over 300. Okay. So we have that. So the next step is we need to find the equilibrium concentrations in the rate equation. So the disappearance of A, since this is a elementary reaction, say K equals Ca minus Cb, Cc by KC. And yeah, you can show that KC is going to equal K by K by KR. Do small r. Okay, so I mean, that's the rate equation. Yeah, and so then we will have, at the equilibrium, this will equal 0. So then we can simplify this equation to CA minus CB times CC or KC equals 0. Or these should be equilibrium concentrations. So then we can find Kc. So Kc is then equal to Cb equilibrium, Cc equilibrium divided by Ca equilibrium. Okay. So now we need to determine what these equilibrium concentrations will be in terms of the equilibrium conversion constant. So we're fed pure A, and so Ca equilibrium is going to be Ca0 times 1 minus Xa. And similar, and so for Cb equilibrium, no B is fed, so and it's stoichiometric ratio 1 to 1 with A, so Ca0 times Xe. And same for Cc, it's 1 to 1 with A, it's a product. So and there's none fed, so Ca0 times Xe. Okay, so now we can plug these into our equation for Kc. So Kc will equal Ca0 Xe, Ca0 Xe divided by Ca0 1 minus Xe. And so we're going to move this to the other side, and then we'll get a quadratic formula. So Kc times 1 minus Xe equals Ca0 Xe squared. So this will go 0 equals Ca0 Xe squared plus Kc Xe and then minus Kc. So we just plug in the quadratic formula, and Xe will be equal to Kc plus or minus Kc squared minus 4 Kc Ca0 and divided by 2 Ca0. Okay. So we know that this has to be the equilibrium conversion has to be positive. So we can actually, if this square root has to be positive, so in order for this to be positive, we know this has to be positive. We can't have that negative sign, so it'll just be the positive. So that will be our equilibrium conversion. So for part B, it asks at 300 Kelvin to calculate it. So at 300 Kelvin, we're given actually that the Kc equals 1. So otherwise we would need to use the equation up above to plug in the temperature and calculate it. So then just plugging in Kc1 and Ca0, you know Ca0 is 2. So we can plug that into this equation and we'll get Xe equals -1 plus 1 plus 8 divided by 4. So this will equal 1/2. Okay. And for the last part, it asks about if the reaction is endothermic or exothermic. So for that, since the specific heat of reaction is negative, that means it's going to be exothermic. And then for whether the Kc increase or decrease with temperature, we just look at the equation up above we had for Kc. So Kc equals Kc 300 times the exponent of delta H reaction over R times 1 over 300. Let me zoom. 1 over 300 times 1 minus T, 1 over temperature. So see what is increase or decrease is easiest just to do. So we say, so temperature is increasing, so this value is going to decrease. Because we're dividing by larger temperature, that's going to decrease. So then this value is going to increase because we're subtracting by a smaller number. So then this value, so this is remember this is negative, and so because this increased, so in these parentheses increased, and it's multiplying by a negative, so the exponent times a bigger negative number is going to be smaller. So our Kc is going to be smaller. Okay, and so that's it for that problem. And I'm just going to make a new video for the next problem.